Thank you. I'm going to talk to you today about my discovery of the Simulacrum System and how it led to a new understanding of space, mass, and the periodic table. My name is Dr. Craig Byrdwell, and I'm a research scientist studying the chemistry of fats and lipids. So these are fats, these are what I study. These are triacylglycerols or triglycerides. Tri, because it's 1, 2, 3 carbon backbone here. Triacylglycerols, this is a glycerol backbone with tri fatty acids hanging off of it. And this has double bonds between this and that, and this is sites of unsaturation. So these are polyunsaturated fats. This one is a monounsaturated fat. That's oleic acid, like in olive oil. This is linoleic acid, L. So this is linoleic, oleic. So this is the kind that comes from like soybean oil, and this is mostly in olive oil. But these are common fats that occur in all different types of fats, including our bodies. And so when I do mass spectrometry of these, that's my analytical technique, mass spectrometry. We charge these molecules, we just get an ion. That's a hydrogen with a charge, that's called a proton. So add that to this oxygen-rich, this electron-rich oxygen, and you get a protonated molecule that's now got one charge over the whole molecule. And that charge is enough to use as a handle to be able to do mass spectrometry, where we guide the molecule through the mass spectrometer to the detector, and it only comes off at a frequency that corresponds to this exact mass. So when it goes through the mass spectrometer, we fragment it in order to get big pieces of it. And so being a mass spectrometrist is being a puzzle meister. So you put the pieces back together and figure out what the original molecule was. So these are the diacylglycerol fragments, two fatty chains, diacylglycerol fragments. 1, 2, this is an LO and an LL because there was 2 L's and 1 O, so there's 2 ways to get LLs, but only, 2 ways to get the LO, but only 1 way to get the LL, so there'd be twice as many of this one as there are of that one. Anyway, that's diacylglycerol fragments that come from the triacylglycerol. Now, actually, one last thing is that the amounts of each of these things tell you, the amounts of this fragment versus that fragment tell you where the fatty acid that was lost. See, there's one missing, it was lost. And which fragment is left tells you where the one that was lost from. And so that's important because the one that's in the number 2 position here is harder to lose. It's energetically disfavored to lose that one. It's harder to lose. The other ones fall off easier when you're fragmenting. And it just so happens that that's the same way that your body treats fats when you eat them. The enzymes gnaw off the outer fats first, and so those are taken off in your gut, and then the one in the fat in the number 2 carbon position is conserved, and so it goes into the fat building mechanism of your own body to build new fats. And so whatever the fatty acid is there, that's why fish oils and things like that have fatty acid, polyunsaturated fatty acids in the middle that is conserved, goes into your system, into your catabolism system. These are metabolized, chewed up into pieces, and some of those pieces, the pieces go different directions. This goes into your catabolism system to build new fats. Okay, next, and you should get 2 of these fragments for every one of those, just statistically speaking. So the ratio of this to that should be 2 to 1, or if you do it the other way, 1 to 2, or 0.5. Should be 1 to 2 should be the statistically expected ratio if there were no other favoritism. Go ahead. Okay, so yeah, this is just showing ABC fatty acids here, then the linoleic acid is both A and B. So AC and BC are the same thing here. And then you have AB. So this just demonstrates what I was saying earlier. Two ways to get this one, one way to get that one. So this is what a mass spectrum, this is a separation, this is what my data looks like that I publish. And so this is a 2000 IU gel cap. So this is a fat, like a soybean oil type of fat that, so these are triglycerides, triacylglycerols. And so we can look at each of these, and the ones that come out early are the polyunsaturated fats. And then as you go on later and later, it's the saturated fats. So we pull them apart and see how much of the good fatty acids and the bad fatty acids and all of this toward developing better nutritional fats. And so this is what a mass spectrum looks like. This is the intact molecule. On that previous slide, I showed the whole intact molecule with just that hydrogen on it, just a charge. And that's what gives this mass right here. That's the protonated, the MH is the molecule plus that extra H that gives it a positive charge. So now we got a handle, we can tell its mass is 875.7. And then it breaks into those fragments, those DAG fragments, and here are the DAG fragments. So these tell us about the structures of the fragments, so we can tell exactly what that molecule is. It's linolenic, 18,3, linoleic, 18,2, linolenic, 18,3. And so then each of these is a different fat. And each one of them, as you go from, these are polyunsaturated fats, 18 carbons long with 3 double bonds, 2 double bonds. So compare that to something out here that only has 2 double bonds, 1 in this chain. So this is oleic acid, that's 18 carbons, 1 double bond, 18 carbons, 1 double bond, and then a saturated fat, 18 carbons, no double bonds. And you get very little of the protonated molecule and mostly the DAG fragment. Compared to this, you get mostly this. So depending on the amount of unsaturation, it tells you how much of the molecule. So if you know the ratio of these to those, you'll automatically have an idea of how much unsaturation it has. So I made that a critical ratio of the protonated molecule to the sum of all those DAG fragments to immediately give you an idea of how, if it's a very high ratio, then it's polyunsaturated, very low ratio, it's monounsaturated, and this MH will actually go to 0 for saturated fats. It can actually be a value of 0, and then you know you got a saturated fat. Next. So then, go ahead, and I was just showing that as the diacylglycerol fragment goes 1, 2, 3, 4, it goes up and up and up until it becomes the base peak, and this goes down until it's smaller. Okay, so I made these critical ratios that told me information about the fats and how they were metabolized in the human body. First of all, the MH over sum of the DAG, it's the last slide we showed that just showed it correlated to how much polyunsaturated fatty acid, sites of unsaturation were in the molecule. The more of them, the higher this number, the less of them, the lower this number. And for a triacylglycerol that has all the same fats, all just one type, AAA, then that's the only ratio you get. Now for a type 2 that has ABA, then you get 2 ratios. You get AA and AB. And so you can do the ratio AA to AB or AB to AA. Well, I chose AA to AB. And then you also get this that tells you about, so this one always tells you about the degree of polyunsaturated fats in it. This one tells about their location, because the fat that's in the number 2 position, if it's ABA and B is in the number 2 position, then the fragment resulting from loss of B would be the smallest fragment because it would be less abundant. So you can deduce some structural information from that. And if you have all three different A, B, and C, three different fats, then you have three different ratios. You have the polyunsaturated ratio, and then this one is the AC. That would be the outer two. Again, that is the ratio of the one lost from the middle versus the ones lost from the outer. So this is equivalent to that, but just using three different fragments. But these two fragments basically behave the same. And then to completely fill out the set, if you have three fatty acids, then you end up also wanting the ratio of those last two, one to the other. And there's no structural trends that were reported about that yet, but when we just construct it so that it's less than one, then we actually found some trends in it that had never been reported. So go ahead. So this is what a mass spectrum looks like for a type 1 triacylglycerol. You have nothing but the protonated molecule and that one single diacylglycerol fragment. For a type 2, you have the protonated molecule and the two different diacylglycerol fragments. And for the type 3, you've got the protonated molecule and three diacylglycerol fragments. So the critical ratios are made from these. Now these are all idealized at 100% or a value of 1, but they actually are less than 1, and the ratio of these to those depends on the degree of unsaturation, and then the ratio of this one to that one depends on whether it's the 1-2 in the 1-3 position or one of the 1-2 or 2-3 positions. So this is the behavior then. This is a plot of the behavior of that one that follows the polyunsaturated fats. It's that if it has 0 sites of unsaturation, the ratio, that first critical ratio is 0. Like I said, 0 at 0. No unsaturation, you don't get any protonated molecule whatsoever. And then as you go up to the monounsaturated, diunsaturated, so then you start getting more unsaturation. Then by the time you get to the 4th and 5th sites of unsaturation, then it's going to flip from being a mass spectrum that has a small protonated molecule to now one where the protonated molecule is the base peak, the largest peak. And so that flip occurs down here in about 4 to 5 sites of unsaturation. And after that then, so you can see it's kind of a sigmoid shape. And so I modeled it to have this equation, a sigmoid, just a kind of a first approximation of a model. Go ahead. And this is that second ratio, the one that I told you about. If the chain is lost from the middle, it's disfavored. And so on this chart right here, this is the amount of ABA. So that's the 1-3 out of the sum, out of the combined other two. And this is the AA to AB ratio. So if the AA ratio, if it happens that the B is in the middle position, the AA is going to be extra small. So it's going to be smallest wherever you have ABA. And so here it is right down here at its very lowest position for this fatty acid O-lin-O, that's 18.1, 18.3, 18.1. It's got a very low value of 0.29 if it's ABA. Now if it's AAB, then you have more than one way to get an AA, so that ratio goes up. And if it's nothing but AAB, then it's a high ratio. If it's OO-lin, or the A is O and the B is lin, so ABA would be O-lin-O. Up here, it's 0% of the O-lin-O. It's all OO-lin, and it's got a value of 0.72 ratio of AA to AB. So this ratio, and advance once, the value by, so the statistically expected value, if there were no effects due to position or unsaturation or anything, is just 0.5, 1 to 2. And that's what the S is, 0.5. But in reality, if it's an ABA, it has this less than statistically expected. If it's AAB, it's more than statistically expected. So you can look at this, you can get your data from the mass spectrometer, look at the ratio of your fragments, and that ratio will tell you which of the, what's called the isomers. They're all the same number of carbons and hydrogens, just arranged in different ways. And so this tells you which isomer you have, whether you have the O-lin-O or the O-O-lin isomer, or some mixture of them. It can be anywhere in between. Advance one more time. In this example, the observed O-O over O-lin ratio was 0.427, one more time. And that gave a ratio of 68.1% of the ABA or the O-lin-O. And so here are then the critical ratios. The sigmoid shape is the one that for this unsaturation. So that's all of these give the same sigmoid shape. This is the one for the regioisomer, telling if it's on the outside or the inside or in the 2 position. And that's the linear line that it bounds between above and below statistical. So those are the critical ratios that I developed that squeezed out the information for me from the data that I had and I wanted to give information from. So if you'll notice, these ratios ended up being nested into one another. So the sum, the denominator of this ratio ended up was the sum of the following ratio, the succeeding ratio. And then that means then that the sum of all of these will be the sum that's in that denominator. So the sum of these then becomes the denominator in that ratio. And then the sum of everything is the sum of all ions. Go ahead. Okay. So you can see that it wasn't super conscious doing it, but I ended up building a set of equations that had the property of self-similarity. Each one was nested into the one above it, just like the Fibonacci series is. So the critical ratio, the critical ratios here had critical values that were kind of inherent, built into the construct. They could, if they were equal, that's like a critical value, critical point. If they're both equal, then that's 1 to 1. So that would be 1 to 1 if it's, so it has a critical value of 1. And if it's a ratio of less than 1, then MH over DAG is case 1. If it's greater than 1, then it's case 2. And so it's polyunsaturated, it's in this range. If it's saturated, it's down here and even going down to 0. Go ahead. So that's the saturated tag that can go down to 0. So this is the picture of the bottom-up solution. So what this is here's an axis here that is the MH over sum of the DAG. You plot that 0 to 1 here on that axis. And then on these axes, they could theoretically be anything from 0 to infinity, but we know they run in certain ranges. I showed you that plot where it moved from this regioisomer at 0.29 to that regioisomer at 0.72. It's a range that those fragments are going to appear in. And so here's that range. So from 0 to 1, the AA to AB ratio would appear somewhere between the 0.29 and the 0.72. These are the pure regioisomers. And when you analyze your regioisomer on that scale, then it tells you where you are. For instance, that's 68.1 of the isomer that was in the example. So that's what this is. This is the triacylglycerol lipidome, where this is the MH over the sum of the DAG ratio, and this is the regioisomer. So there are 2 ratios plotted on this graph. Go ahead. So, and then there's a built-in inherent critical value of 0.5 or 1 over 2 here, because you've got the way that the DAGs worked. I showed you how the statistically expected is 0.5. And then anything over 1 is automatically the protonated molecule base peak. So, and then the critical limit, what the actual, when you decide which one's actually going to be the base peak or not, depends on the size of your diacylglycerol fragments and how many there were. If it's a type 1 or type 2 or type 3, how much each one is, you get this critical limit that determines whether you have an MH as the base peak or one of the DAGs as the base peak. And then for the regioisomers, this is that chart that I showed you earlier where it's going between the two values. And so based on this, you can tell which regioisomer, where the A and the B are, and if the B is polyunsaturated, then when you eat it, will it be conserved or not? Okay, we'll skip past this. You can make, okay. So enough of this. I made the structure. This is the bottom-up solution, and it had cases. And within those cases, within the case for the MH over the sum of the DAG, there was another case for the next ratio. So you had 1 point in or 2 point in. And then for the type 3 tags that have 3 fatty acids, yeah, it's even one more complex. So let's skip past that. All right, so this was the critical ratio. Now, when I was doing the mass spectrometry, I wanted the MH over sum of the DAG as my first critical ratio because, as I told you, for saturates, the MH could go to 0, right? And so if it's going to go to 0, then you need it to be in the numerator of a fraction instead of the denominator, because if the denominator ever goes to 0, then that's irrational. But the numerator can go to 0, that's fine. It just becomes a 0 value ratio. And so so I told you that I used the MH over sum of the DAG ratio. So the road not taken is the one I didn't choose, which is the other possible ratio I could have used, but I didn't, is the sum of the DAGs over the protonated molecule. I didn't choose that because this could go to 0. But for another type of mass spectrometry I do, electrospray mass spectrometry, you can get a protonated, you can get an ammonium adduct, instead of protonated, it'd be ammonium, and absolutely no DAG fragments whatsoever. Just nothing but the one. And so in that case, if the DAG fragments can go to 0, then you would want to use this other, the inverse equation. And so although I discovered the bottom-up solution, it was half of a bigger picture. And the bigger picture is what ended up becoming the whole simulacrum system. And the simulacrum system contained all possibilities, whether chosen or not chosen, selected, not selected, built, not built, found, not found, discovered, not discovered. So go ahead. All right, so enough of this. This is, so electrospray ionization, I just show how that you could have a mass spectrum where the DAG fragment goes to 0, and so you'd need that inverse ratio to use as your main ratio in order to keep it bounded and rational. So the bottom-up solution that I used, the MH over sum of the DAGs, was half of this octahedron. It was this part out back, and then on the top, and then this part down on the bottom. And when you include the opposite, the inverse ratio that you didn't select, well, then it's those other two halves of the octahedron that you didn't select. And so by then having the simulacrum where you see all possibilities, all solutions, whether selected or not selected, then you see the whole simulacrum shape. And it's an octahedron where the lower 4 are the 4 cases, the 4 possibilities of case 1 solution using either ratio. And then the equatorial plane is the equality plane. It's everything is equal to 1, because in each solution, case 1 and case 2, case 1, A less than or equal to B. Case 2, A greater than or equal to B, and so they could meet at the equality. And the above four sides of the octahedron are the case 2. So 4 case 1, 4 case 2, and 4 equalities. So that is the shape of the simulacrum. And this is a simulacrum. So this is the first general form of a simulacrum. So using the MH and some of the DAGs just as examples of A and B. You know, just any old things, A and B, anything. So you just first state the simulacrum, so you state the sim sum of MH and sum of DAGs equals also the mathematical sum of MH and sum of the DAGs. And that equals, first of all, you've got the pos2 obs, possibilities to observe. There are always 4 pos2 obs. You can observe the first thing directly, or you can observe or you can observe it all. If you have a complete data set, you have all of it and you construct what you want. If you don't have a complete data set, you take what you can get. So you can have the one value directly, the other value directly. You can have just the ratio of the first value to the second, or you can have the ratio of the second value to the first. Those are the 4 pos2 obs, 2 direct observation and 2 indirect observation, 2 ratios. So those go into the simulacrum, and here are brackets on the side, and I like to say that this is Schrodinger's box. It's that all uncertainty can occur inside that box. Things can switch back and forth, above the equality, below the equality, anything can happen in Schrodinger's box. But at the end, you have to select a ratio and spit out an answer. And so in the case of mass spectrometry, the way that we do it is we classify, I classify everything and narrow it down to determine which one is going to have a value of 1, which one's going to be the base peak. And I have that 1, I select whichever solution has the 1 on the outside here, and then just throw everything else away, because if you have 1 on the outside here, it's super easy. It just that 1 cancels, simplifies out, and you have your solution right here. And so it always ends up simplifying to 1 plus a ratio or 1 plus 1 over a ratio. So basically that's the way the simulacrum, you choose the solutions that are going to lead you to the easiest answer of 1 plus a ratio, 1 plus over a ratio. So go ahead and keep advancing there. So now this, actually go back one more. Okay, so that's the first general form. That's the first general form of a simulacrum with no specifications whatsoever. Those can be any values. So go ahead now. Now I jumped to, instead of going to the first specified form, in this slide deck I went to the second specified form. This is the mass spectrometry simulacrum, because it's got 2 specifications. In mass spectrometry, no value can be greater than 1. In a mass spectrum, it's a picture of going from 0 to 100% relative abundance, and then the mass is the x-axis. And so nothing can be greater than 1. But the second rule is something has to be 1. You know, whatever the tallest value is set to 100%, and everything else is relative abundance to it. And so advanced wants 1 value is 1 in mass spectrometry, and no value can be greater than 1 in mass spectrometry. So when you determine which one is the base peak, for instance, for case 1 here, if DAG is on is going to be 1, then you would select the solution where the DAG is replaced with the 1, and then that'll just cancel out, and you have 2 simple solutions here. Or if it was case 2, and you would find the protonated molecule that was 1, and when it was replaced with 1 in case 2, then that would cancel out. So if it's case 1, you select these 2 based on the DAG. If you select case 2, you select this based on MH, and you get simplified solutions based on just that ratio. So that was the mass spectrometry simulacrum. Go ahead. Okay, so I'm just showing that you just eliminate all the other ones, and these simplify further, so you just get 1 plus a ratio and 1 plus 1 over a ratio. All right, so that's really how that's really in the bottom-up solution, in the updated bottom-up solution that's published in the journal. Now this one is in the journal Analytical and Bioanalytical Chemistry, but what you end up with is the two solutions. Here's the critical ratio and critical value of that ratio to be able to categorize it as case 1 or case 2 with the DAG base peak or the protein molecule base peak. So it's either that ratio or 1 over that ratio. All right, so you can then just generalize it to forget about mass spectrometry, just any A and B. Anything that you can put a symbol on, any name, number, symbol, anything, you can put it in here. And the simulacrum is, sum of A and B is equal to the mathematical sum. You got your pos 2 obs, the 2 that are direct observation, 2 that are ratios. Case 1, case 2 inside the brackets. So this is your Schrodinger's box. And so whatever meaning that you hang on to A and B, that's what's called the interpretation matrix. So the simulacrum builds right into its construct consciousness. So however you define these is what they are. So the simulacrum is a total consciousness base. It's based on unit definitions. And so we're going to get to the unit simulacrum in just a minute, and let's go to that then. So the first specified form of a simulacrum, the other was the full general form, no specifications whatsoever. Free range A and B could be anything you can write down, unrestricted. Now let's place one restriction, that one value is 1. That's the first restriction. So the first specification that we're going to put on the full general form, and that's going to make this the first specified form of a simulacrum, also known as the unit simulacrum. If we specify that one value is 1, that's a unit. One value is 1. So you got A and you got 1. And so that is, go back to that for a second. This is a unit simulacrum. And the only specification is that one value is 1. And so case 1 is that A is less than 1. Case 2 is that A is greater than 1. So case 1, A is less than or equal to 1. Case 2 is greater than or equal to 1. And so if A equals 1, it's both case 1 and case 2. So that would allow theoretically a quantum mechanical superposition. All right. So that is the first part of the talk on how I discovered the simulacrum. And it showed how it came directly from the mass spectrometry of my work. And so now we're going to take that, we're going to go ahead and cut this video right here, take a break, and we'll pause it and come back after a brief break.